Hello, my name is Matthias Bentert and welcome to the talk on our paper using a geometric lens to find k-disjoint shortest path. This is joint work with André Nichterlein, Malte, Renken and Philipp Zschoche. We are all from TU Berlin. So what is our paper about? Let's start with an example. Let's say we want to travel from A to B in this network. And for obvious reasons, we want to do so as fast as possible, meaning we want to take a shortest path. We have different options. We could take this way above here, below, or some zigzag way. Let's just say we decide for this one. And now there is a second person that wants to travel from C to D, also with an as short way as possible. So this would be one example. But there are certain scenarios in where meeting on such shortest path is not wanted. One possible example for this, I don't know, let's say there is a global pandemic. So if we want to avoid these kinds of overlaps, then we have a few options. So one way is that the second person chooses a slightly different way, but this is then not optimal for him or her because this way is longer. Another possible way would be that I change my initial route. As discussed before, this is also a shortest way. And now also the second person can get from C to D in 2 steps. So this leads to the following problem. Disjoint shortest path, we are given an undirected graph and vertex terminal pairs SITI. So in our example, A and B would be one terminal pair S1, T1, and C and D S2 and T2. And we want to find path between these terminals such that all of these paths are pairwise vertex disjoint, so they share no vertex and thus also no edge. And all of these paths should be shortest path between the respective terminals. So now that we know what the problem is, let me give you a brief introduction into the problem and also different variants of this problem. And I want to start with the 2 disjoint path problem. Here we only have 2 terminal pairs and we do not require that the solution paths are shortest path. They should, however, be disjoint path. And it was already proven in 1980 that this is NP hard on directed graphs. And rather recently it was shown that it's linear time solvable on directed acyclic graphs, and for undirected graphs it's polynomial time solvable, and we can even find path of minimal total length. So the sum of the 2 path length. For the problem k disjoint path, so not 2 but an arbitrary fixed number k of disjoint path that we are looking for, but still not shortest path, it is known that the problem is solvable in xp time on directed acyclic graphs. Now, adding the requirement of shortest path, let's start with 2 disjoint shortest path. There it was proven in 1998 that the problem is polynomial time solvable on undirected graphs. And this paper already asked whether this polynomial time algorithm can be generalized to an arbitrary fixed number k of disjoint shortest path, the problem variant we are interested in. This n to the 8 time algorithm was recently improved to n to the 6, and for directed graphs it's also known to be polynomial time solvable. And now to the problem variant we are interested in, k disjoint shortest path. Parallel to us, William Lochert showed that the problem is solvable in xp time, so in polynomial time for each constant k on undirected graphs. And we, with a different approach, show that also an xp time algorithm, but with a faster running time. And we also show W1 hardness, and using our slightly different approach from the one by Lochert, we are also able to improve the 2 disjoint shortest path problem on undirected graphs 2O of n times m. In the remainder of this talk, I want to give a brief overview on how our algorithms work. So our algorithm, as the title suggests, is based on a geometric view on the whole problem, and this I want to explain next. So this is the same graph as in our example in the beginning, and now we identify with each vertex a vector, and this vector, each entry of this vector represents the distance to one of our starting terminals, S1, S2, and for larger k also S3, S4, and so on. So if we do this for all the vertices, this might look like this. So for example, this vertex here has distance 3 from S1 and distance 1 from S2. And now we take the vertices and we project them into k-dimensional space. For our example here, k equals 2-dimensional space. And we just place each vertex at its respective coordinates. So for this vertex 1, 1, here, this is this vertex, and maybe other one here, 3, 1, is this one. And then we just connect vertices here by a straight edge. So this then looks like this. Maybe two important things here. First, these vectors do not need to be unique. So there might be multiple vertices at one point here, but this is no problem for us. And second, if we now look at vertex S2, for example, and consider a path like this, then we know this cannot be a solution path. Why is this? Well, the length of the path increases with each edge we take, but the distance from S2 does not increase with this last edge here. So we know that since the path takes an edge that is not going down in our drawing here, this cannot be shortest path. And if we generalize this idea, then we see that all important vertices, or all vertices that might be part of a shortest S2T2 path, can only lie in this gray region here. So to say, in a 45-degree angle from point S2. But we can, of course, do the same for our vertex T2 and get that we have some kind of space to work in a 45-degree angle from here as well, because if we would take such an edge that goes outside of this region, then we have the same, this edge does not increase, the distance does not decrease the distance to S2, but increases the length of the path by 1. So since all important vertices for the second path are in both of these, we get the intersection, that is, we get such a rectangle. And in more dimension, this would be then a hyperrectangle. And we can do, of course, the same for S1 and T1 as well, and their important part would look something like this. Okay, so this is the idea behind our geometric view, and just as a side remark, only because a vertex is placed within such a rectangle does not mean it can be part of a shortest path, as for example this blue vertex here. It is within this rectangle we just described, but it cannot be part of a shortest S2T2 path because it's not a neighbor of T2. So the distance from T2 is at least 2. That's a problem. So with these kind of rectangles, we have a necessary condition a vertex has to fulfill to be part of a shortest S2T2 path, or SITI path, but not a sufficient condition. So now you might be wondering, how do we use these rectangles? And I want to present this next. So we make a case distinction. How do these rectangles look like? If the rectangles are disjoint, then I can just split my graph into vertices that are important for S2, T2 and S1 and T1 and solve these two sub-instances separately. So this is an easy case to solve. A second case might be that rectangles intersect, but the path coordinates of optimal path, and we do not know them in advance, but there are solution paths such that the rectangles overlap, but the paths do not share a common coordinate. In this case, we like to think of the problem as being solvable using marbles. So just assume that someone tells us that the blue path or the solution between S2 and T2 goes through this vertex. So in some sets, it's a marble that's left on the floor for the blue path to collect. Now the problem again becomes easier, because if we know that we need to visit this vertex, then we can have the same idea of these rectangles to show that the important parts for S2 and T2 lie in these two blue regions plus this one vertex. And in the end, we of course just iterate over all possibilities of this blue marble. A third case is that the path coordinates intersect, but just in a single point. In this case, we can just guess marbles again, such that either if the intersection is at a non-integer point, we have 4 marbles, otherwise we just say there are 2 marbles in the middle, and red uses one of them, blue uses the other one, and then we get these disjoint rectangles again, and they are easy to solve. And the final and most complicated case is that 2 paths share multiple points. So in this case, we again guess marbles, such that, and here this black dot just represents, here we guess a marble for blue and for red, and the same here. And now we have the easy parts drawn in blue and yellow, blue and red, sorry, and we have the difficult path. So here we have the same coordinates, and these vertices are somehow important to both blue and red. But in this case, we can somehow orient the edges from one point to the next, and now we are left with the problem of 2 disjoint shortest path on a DAG, and there is a linear time algorithm that I referenced before for this subproblem. And now by just improving on not guessing too many marbles here, but in fact just guessing 1 marble and then using the idea of having easy to solve parts and 1 part that can be solved in linear time using the referenced algorithm, we can solve 2 disjoint shortest path on undirected graphs in O of n times n. So O of n for guessing the correct marble, which will be one of those, and then having a case distinction that I do not want to go into, but it's also not that complicated, and then solving all of the remaining instances separately. Okay, and with this general idea, we have solved the case of 2 shortest disjoint path, and now we want to generalize this to multiple path. And our general approach is to use marbles as before, to then have subpaths such that either we can use these direction idea, so there is a common color. Let me go back, this green path here, so we have one of the dimensions in which all of the paths are monotone. In this case, both of the paths are monotone in both directions, but in general it's enough to have just a single common dimension, then we can use an algorithm for k, disjoint shortest path on a deck, which is solvable in xp time, as seen before, or subpath have disjoint hyperrectangles. So either we can solve them separately or we can solve them using the algorithm for decks. That's the basic idea. But there is a problem, and this problem I want to demonstrate now. Let's say we guess marbles as we have done for each two of them, we guess marbles as before. And let's just say it turned out to look like this. So this here stands for, okay, here we have some rectangles that are disjoint, and this here is somehow the green part where we have a deck for two path. And the same for this part here and this part here. Okay, but now let's consider this first part here, and we know it has to be in the same dynamic or in the same deck as the vertices for this subpath of the blue paths here. Then we know that this has to be also in the same deck as these yellow vertices here, because they share a common coordinate with these blue vertices here. Again, since there's some overlap here, this part also needs to be on the same deck, and this part and this part. But now we have a problem, because this part here is just in the yellow-green dimension, so to say, monotone. So each part is, of course, monotone in its own color. So let's say in the green dimension, this one here is definitely monotone. And since it intersects, so this here is this deck idea again. So here it's monotone in the green and in the yellow dimension. And this part over here, by the same argument, is monotone in the red dimension and in the blue dimension. But these two have to be solved on the same deck, but there is no color that is common to both of those. So this was one of the main obstacles we had to overcome. Our solution to this problem is to introduce even more marbles. So here you see even more marbles. So the idea is, if we transfer or have that the red and the blue share common blue-red coordinates, then we somehow keep track of in which colors is a certain subpath monotone. This one here, for example, in the red and in the blue one. And now if we try to further transfer these ideas, so this one is now already monotone in red and blue, and we check, okay, can we transfer the red color even further? So, and if we can do so, then this path in the bottom here will not be only monotone in yellow and blue, but also in red. And so for this sub-instance here, so we do not have a marble for this, but we again just guess, okay, is this whole path here also red monotone, or is only a subpath here red monotone and has the same red coordinates as the subpath here, or can we distinguish between the two just by the red coordinate? These are the three possible cases. So in general, there is a subpath which can be empty, where we can transfer all the colors. So now this one is monotone in red, blue, and yellow. And the main observation we have here is that if we want to transfer the red color to other paths, we can do so via permutation. So we can go from red to blue to yellow, or from red to yellow to blue, or something like this. But we cannot ever go back in the sense. So it would not make sense to transfer the red color from here to the blue path, because we already know that the red color gives us that these two paths have the same red coordinates, and so there cannot be any other path here that has the same yellow and red coordinates as this part here. And now, how many of these transfers can there be? Well, we can start with k colors and we can transfer them to k-1. And then in the next step, there are k-2. So in total, there are at most k factorial of these transfers. And for each of these transfers, we only need to guess a constant number of marbles. And this leads to our main result. K disjoint shortest path can be solved in n to the O of k+1 factorial time on undirected graphs, and for k equal 2, again on undirected graph, we can solve it in n times m. Again here, this was just guess one marble, and then some case distinction. And for the other, so for the general k, these k O of k+1 or n to the O of k+1 is for guessing the marbles. Then we can, in polynomial time, divide them as we wanted into cases that we can solve separately, and building DAGs that can solve those that have a common color. And then for solving these DAGs, we again need something like n to the k+1 factorial time, because that's the number of paths we put on each of the, or at most put in each of the sub-problems. So solving on DAGs takes roughly time n to the number of paths that you want to route. And with this, I want to conclude my talk. So we have seen a lot of marbles. We have started with the problem description of routing k disjoint shortest path. We have introduced our geometric view on the problem and the different cases of how we guess marbles. Then we have seen the problem and also the solution for generalizing our approach to more than two paths. And with this, I want to come to some open problems. So using ETH, we can show that the problem is probably not solvable in n to the little o of k, but this is sublinear, and we are at k factorial roughly, k+1 factorial. So there's quite a huge gap, and whether something polynomial in k is somewhere in the middle is possible, we don't know. Then our approach does not work for directed graphs, so there a completely new approach is needed. So this is an interesting open problem. Weighted graphs, so our approach should work for weighted graphs, but for example, directed weighted graphs would then be a whole other problem. And finally, coming back to our motivating example, sometimes it's not important that the path intersect or not, but that not two people are at the same position at the same time. So this leads to the questions of k disjoint shortest path on temporal graphs. And I've recently learned that there are some first studies in this direction, but they are not published yet. And with this, I want to thank you for your attention and have a nice archive. Thank you.